Hi, I'm Wesley,
And I'm Justin.
and for this project, we're demonstrating how GPU acceleration can transform K-means clustering performance. And we implemented the same algorithm across three frameworks, specifically the CPU with NumPy, the GPU with PyTorch, and custom CUDA kernels to show the different performances.
All right, so let's go over our code. So first, we install PyCUDA as shown here. This is the GPU we used. This is our CPU we used. This is the PyTorch version, and this is the PyCUDA version we are using. So we basically generate our dataset using the scikit-learn's make blobs, and we're doing it from dataset sizes ranging from 1,000 to 200,000. And this is what our dataset looks like originally. For our first implementation, we're using the base k-means CPU function. So what this k-mean does is first it calculates the distances between every point and every centroid. Then it assigns each point to its nearest centroid, and then it updates the centroids. It keeps repeating its process until the centroids barely move, then we stop there. But the problem with the base function is that the distances to calculate all the distances is computationally expensive. Like for example, if we have 100,000 points and five centroids, that's 500,000 distance calculations per iteration, which is a lot. Our next implementation is using PyTorch, which uses GPU. So based on this line, we leverage GPU acceleration automatically if available. The key difference is in the PyTorch implementation, we have the torch.cdist function, which is optimized for GPU and calculates all the distances in parallel. The algorithm logic stays the same, but execution happens on thousands of GPU cores simultaneously. Up next, we have our PyCUDA implementation. So for maximum control and learning, we decided to implement custom CUDA kernels to better our understanding. And this required us to, to do memory management and kernel design. So let me talk about the calculate distances function I implemented. So, so as you see, each thread processes one data point and calculates its distances to all the centroids in parallel. And with thousands of threads running simultaneously, this drastically reduces computation time.
Okay, and for the assign clusters function, we first need to do a bound check, which is checking if the index is greater than the points, and if it is, then you just do return. And this line is to first initialize the best distance and the best index. After that, you go through a for loop. Um, and in this for loop, each thread handles one point simultaneously, and it calculates the distance for each point, and as it assigns it to the nearest centroid.
In here, we use the source module to compile our CUDA kernels, and then we get our references to each of our kernels, calculate distances, and assign clusters. We manually allocate the memory shown here. We then copy the dataset to the GPU, which is from host to device. We then get our grid and block dimensions. And in our for loop, we copy our current centroids to GPU. We then call our calculate distances kernel. We also call our assign clusters kernel. We then copy the cluster assignments back to its host. So basically, it's device to host. And similarly, like the previous implementations, we update the centroids on the CPU, and we keep repeating that until the centroids barely move. Then we stop, and then we free our memory.
Okay, so for our results, we have the results of the three implementations, the CPU time, the PyTorch time, and the PyCUDA time. And the time represents the time it takes to run the base k-means function. So as you can see here, for a smaller data set size of 1,000, the CPU time comparing to the GPU times, which is the PyTorch and the PyCUDA, the gap isn't really that big. But as you go to the larger data sets, for the 200,000 data set size, you can see the CPU time goes above 2 minutes, which is really long. Whereas the GPU times are still below 1 second. Um, so yeah, this is because the CPU calculates the distances one at a time, while the GPU versions, they all calculate the distances in a parallel. So you can see here for the CPU k-means results, we have 5 clusters with 5 centroids. Uh, Over here we have the PyTorch results. You can see here that the clusters and centroids are different from the CPU results, but this doesn't really matter because we're measuring the performance of the three implementations. And you can see similarly here, the PyCUDA also has the similar results to the PyTorch. And over here, we have a bar graph comparing the PyTorch speedup and the CPU version. You can see here for smaller data sets of 1,000, it's only faster by 1.9x. But as you go on to larger data sets, such as 100,000, it's faster by around 3,200x, which is really big. Um, Going down to the PyCUDA versus the CPU, the PyCUDA and PyTorch are both GPU versions, so they will result in similar outcomes. So you can see here. And going down to PyCUDA and PyTorch, we can actually see an inverse in results, which is interesting. Um, but we do know that the PyCUDA and PyTorch, they are both using the GPU. Um, so yeah. And this is performance comparison of the three implementations. We can see the CPU implementation. For a 1K data set, the time is like a little bit above 0 seconds, but as you go on to the 200K points, the time is above 140 seconds, which is really long. Whereas you go to the PyTorch and PyCUDA implementations, the all the data sets have the time under 1 second. Specifically for PyTorch, it's under point 12 seconds, and for PyCUDA, it's under or around point zero 2 seconds. And yeah, that's our presentation.